Hello everyone. Welcome to a follow-along introduction to Rust. My name is Savani. This is a re-recording of a talk that I gave at the Rust NYC Unconference in December of 2025. If you want to follow along, the easiest way to get started is to install Rust via rustup, listed right there, rustup.rs. If you're on Mac OS, you'll probably also need Xcode. If you're on Windows, it could be even trickier with Visual Studio, as well as the need for some extra support libraries. A little bit paradoxically, I believe those support libraries include C and C++ support, but just be sure to find and follow proper documentation. Once you've done that, you can then install, or you can then clone the repository listed here, git.luminescent-streams.com, Rust NYC 2025 Unconf. If you are running on Linux, installing Rust is pretty easy. If you are using the Nix package manager or Nix OS, you don't even need to install anything. You just need to use the flake.nix that is available there in the repository. Once you have all of that going and you've entered the repository, the last thing to run to make sure that you are ready to follow along is cargo install cargo-watch. Now, if you don't want to write the code yourself as you follow along, feel free to just watch the video because I'm going to be live coding all of everything that I'm going to be presenting. And finally, there is an extra branch, the solution branch in the repository, which shows an annotated solved version of the program that we're going to be writing today. We're going to take just a moment to talk about some of the benefits and weaknesses of Rust. First of all, we have performance, which is similar to C and C++. This is a fully compiled language, and it is very well optimized with the developers constantly trying to make it better. That said, performance numbers can be a little bit ambiguous given that sometimes some algorithms will hit particular strengths or weaknesses of a language, and sometimes it depends on whether the people who are optimizing the application can actually hit exactly all of the right elements to perfectly optimize it. We have an expressive type system with a very powerful type inference engine. This inference system makes it easy, or relatively easy, to write aliases for data types that are then incompatible with one another, so that you can, for instance, as I'm doing in some of my own applications, write multiple different UUID types for different object types and ensure that methods can never take a UUID of the wrong object type. We get memory safety, and we get memory management without the cost of a garbage collector or the risk of null pointers. We have a vast library, which, as of today, has roughly 217,000 crates available on crates.io. And then we have absolutely the best error messages in the business. Most of the error messages even go so far as to try to help you solve the error and to pinpoint errors that might not have occurred at the place where the error is detected. This is especially useful when curly braces start getting involved. There are some weaknesses to the language. It is a heavier language than something like Python or even Bash. It can be verbose. The memory model is challenging, and the verbosity is a consequence of the memory model. There are times when we have to copy data explicitly because in places where we would not expect to in other languages. This challenge of the memory model, though, is the price that we have to pay for the memory safety that the language gives us. Finally, when we start reading libraries, some libraries have very abstract type signatures which can be very difficult to reason about unless you are deep into category theory. Now, where have I used Rust? In many different places. I have built a desktop GUI application. This one is a fitness tracker that I have been using for years. A web app that is currently under development. Here we see two different views into the web application. In this one, both the client running in the browser and the server have been written in Rust. I've done it with embedded programming, where I have written applications that can run on a Raspberry Pi Pico, or specifically the RP2040 microcontroller, which you can see embedded directly in the middle of that green board. And then, finally, I was a developer at 1Password for 5 years. The 1Password desktop and mobile applications are driven by a Rust library, which probably incorporates about 1 million lines of code. In this presentation, we're going to write a temperature conversion application, command line temperature conversion. We're going to do it in the most pedantic way possible. This isn't because it is the most efficient way or even the way that you would write a program that is this trivial, but because it showcases a lot of Rust's features. Over it, I'm going to be demonstrating test-driven development. I'm going to be giving you an overview of basic Rust syntax. I will show you error processing as we do it in Rust. In my original talk, I tried to also cover the Rust memory model. However, getting into that, it doesn't add much time, but it adds just enough to make this talk too long. So I'm going to cover the Rust memory model in a future talk. To get started, if you are following along, open up the file source/temperature.rs. In a terminal, run the command cargo watch-x test. This should start a loop, which will, every time you save a file in the repository, will cause cargo to recompile the entire application and then run the automated tests. In this section, we're going to go over functions, we're going to go over structures and enumerations, we're going to go over error reporting and handling, and we're going to go over unit testing, which is a lot to do all in one section. The code looks something like this, where we have an import statement here. With Rust, the keyword is use. We have 3 separate templated functions, all of which have this odd call to do. We have a whole lot of commented out code that we will cover in a moment, and then we have directly in the file our automated test suite. Starting out, we're going to start out by defining a temperature data structure. If we run the tests right now, as I've instructed you to do, what you'll see is that we're getting several compile errors because the temperature data structure hasn't been defined. So we need to start out just by defining them. Let's go over the syntax here. The syntax for a structure, you begin by saying struct followed by the name of the structure that you want to use. Optionally, you can declare that this structure is public, meaning that files outside of this one, or modules, as the case may be, but we're not really going to go over the distinction between files and modules in this talk. So suffice it to say, files outside of this one can address the temperature data structure. You'll note that the one field, Kelvin, has not been declared public. This means that files outside of this one cannot reference that field. This is going to be okay in this case because we want to very tightly control what values can actually be there and how values get populated. So we're going to provide accessor methods both for populating the temperature data structure and for extracting data from it. I do want to note that it's perfectly valid in this case in particular to have just an anonymous field, but that's not what I'm doing in this talk because it's just a little bit harder to read. So the very first thing, like I said, pub struct temperature. The name of the field is Kelvin, and its data type is a 32-bit floating point operation. Now, the last thing I'm going to do does involve some magic. The temperature by itself is not particularly usable. There are a lot of standard operations that we'll want to be able to perform on it. They would be incredibly tedious to implement ourselves, and so the standard library includes automatic implementations for a lot of these. The way we invoke those is with one of the only 2 pieces of macro syntax you are going to see in this entire talk. In order to invoke these, we're going to use the pound square bracket, and then in this we will invoke the derive macro. This particular syntax is used only when we are modifying an otherwise completely syntactically correct block of code. Typically, we use this only for structures, but like we can see down here, we have a different version which handles conditional compilation, which we apply to modules, and in this case, yet another one which we apply to designate that this is test code. The actual implementation of macros of this type is quite complicated, and it is not something I do particularly often. And for that matter, I always have to look at examples anytime I do it. But using the macro is quite easy, and we're going to derive several different traits. First, we're going to derive clone, which is a trait which allows you to explicitly copy the data structure that you're working with. We're going to derive copy, which gives us an implicit copy. Clone and copy are very similar in most cases, with the caveat that while copy is always a deep copy of all of the data within the data structure, clone might not be. Clone could be an optimization, especially if there are some elements added to the data structure to allow for data sharing. Next, we're going to add debug, which provides a canonical debug print representation for the data structure. And then we're going to add partial EQ. Rust has the concept of both partial EQ, or partial equality, and full equality. The distinction between them seems to be that full equality checks that the two objects are in fact the same object, where partial equality is simply sufficient that the two objects have the same value. Most of the time you will not need full equality. In this case, we only need partial equality because all we want to do is to be able to check in our automated tests that the structure that we're getting back from our function is the structure, or has the same value as this structure. Now if we save here, our code completely compiles, and in fact the automated test runs. If we scroll down here, we can see that what the automated test is doing is it is asserting that the result of our from K function, as in from Kelvin, is going to return the temperature data structure, which has a Kelvin value of 212 degrees. Now, from K is obviously not doing that. We instead have a placeholder. The other macro syntax that we see is where we call macros that look like functions, and they will always have an exclamation point at the end. These macros, while the derived macros are about reducing boilerplate code and allowing you to do complex derivations on structures, function-style macros are more about allowing you to do things that are normally just not allowed in the language. What you're doing with macros is you are taking a string of symbols, not characters, but actual parsed symbols, and generating a new abstract syntax tree. Let's jump in to function definitions. Obviously, functions follow a pretty familiar format to you. Declare a function with the fn keyword and give it a name. You can optionally declare this function to be public. We're going to declare all of these to be public because all of them will need to be accessed from outside of this module. Declare a list of parameters. In this case, we only have one parameter. And then, if necessary, declare a return value. If you don't declare a return value, the function is not allowed to return anything. If you do declare a return value, the function is absolutely required to return that from every return location. Let's declare the from K function. We're going to start with this one because it's the most trivial. There's no math to be done here. All we do is we construct the temperature. The syntax for constructing a structure is effectively identical to the syntax for declaring the structure. You use the name of the structure, the curly braces, or parentheses if you're only working with anonymous fields, followed by the name of each field and the value that you're assigning to it. This declaration creates a temperature structure. It is also in the tail position of this function from K. Anything that is within the tail position of a block is going to be implicitly returned from that block. Now, if this is a case in which you don't want to return anything, you can put a semicolon at the end, and implicitly the compiler adds a not null value, but a void or whatever you want to call this, just as a designator that there is no data at all to be stored here. In this case, we want to return the temperature. If we run this, we can now see that our test is passing. If I add that semicolon, we're going to get a compile failure because the function says that it's going to be returning a temperature, but it is in fact returning just this void value. And then here's where the help gets really helpful. It actually tells you where to put, or where the problem probably is. So now that we know that this works, we're going to go ahead and implement out from C and from F. Now, because I can make mistakes on this so easily, I went ahead and threw the formulas in here. We said that Kelvin is equal to C plus 273.15. And in this case, we're going to say that Fahrenheit, or Kelvin, is equal to F minus 32 point. Important to include that point there. A bare 32 is an integer, and Rust does not do implicit typing between integers and floating point operations. So go ahead and include the one dot, and it immediately becomes a float. Now, of course, the test is still passing because I'm not actually testing these two functions, and this is obviously incorrect. So let's finish this out. Finish that, and now our test is still passing. Again, we're not testing these. The reason for that is because I don't actually add these tests until we've added some additional features. So we'll add these tests a little bit later. The next thing that we want to do, though, each one of these effectively amounts to a constructor, a function for constructing a temperature. There's nothing special about constructors in Rust. You can have any number of constructors on your or for your structures, and they can be named anything. New is a frequently used one, but sometimes it will be new with additional parameters, or it will be something like this, where it's from F, from C, from K. It is, however, traditional to namespace these functions within the temperature namespace. So we do that by saying that we want to implement some methods on temperature. And all we do is we move them into here. Now, when I save, the code is going to fail because in the test code, as we see right here, from K is being assumed to be in the top level of the temperature file namespace. And we've just changed the scoping of K. So we'll save the file, and here we go. It says that from K is not found in scope. The way we solve that is we just namespace it with the name of the namespace, which in this case is the name of the structure, followed by 2 colons. Save that, and our test is passing again. Now, for the next part, let's start doing error reporting. Temperatures below absolute zero are invalid. They can't exist in this universe. And so for purposes of this library, I'm going to make them impossible to represent. That is the purpose of making the Kelvin field inaccessible. Even though Kelvin can technically, as a float 32, accept a negative number, negative Kelvin values aren't valid, and therefore we want to make sure, therefore we've hidden the internal field and can only construct a temperature from one of these converter functions so that we can just prevent a negative Kelvin. One of the ways of handling errors is to simply panic when the code runs. The way we do that, as you saw, if K is less than 0, we say panic. Temperature below absolute 0. Now, I believe I did write a test for this. I did not. So we'll go ahead and write a new test. We'll say from K minus minus 5. Now, normally this test would fail, as we saw before, but in fact we're going to get a different error message than before. In this case, again, we get a panic statement, But in this case, the message about the panic is temperature below absolute zero, which comes directly from this macro. That's one way of doing things. It's not generally considered the correct way of doing things. Panics are rather difficult to catch. Even if you wanted to use panics for all of your error reporting, most developers that might consume your library won't expect it. And because panics are difficult to catch, doing local error handling can then become cumbersome. Nevertheless, there are some cases in which panicking is appropriate. If it truly is a completely off-the-wall, this situation shouldn't ever be possible to happen, then you can call panic. To do is a very common one, as you saw to do in my code in several different places. That's simply a way of saying that this area of code still needs to be built. If you hit a to-do, the message that you get will be a panic, but it's going to be a slightly different description as to why it panicked. Similarly, you use unreachable, which again, same procedure, slightly different message, but you use unreachable to indicate that this is an area of code that you thought shouldn't ever be reached at all. And we're going to see one of those later on. And then unimplemented is sort of a generic one that you can use to say, well, you were supposed to implement this function and you just didn't. It's effectively the same as to do, but has ever so slightly different nuances in meaning. That said, in order to get to the proper way of doing error handling in Rust, we have to talk about enumerations, because that is actually, or enumerations are at the foundation of how we do error handling. Enumerations in Rust are full first-class citizens. As you get into them, if you're familiar with Haskell, you'll find that Rust enumerations are effectively the same as Haskell data types. In this case, we have an enumeration that can represent 3 different error types. One of them, the one that we've already seen that we want to use, is below absolute zero. But later on in parsing code, I'm going to introduce an invalid temperature string and also invalid units. Whenever you want to construct a value or instruct a enumeration value, the syntax is the name of the enumeration, the double colon to indicate that you are scoping into the enumeration, and then the name of the variant that you want to use. Now, enumerations are definitely more powerful. I said earlier there are no null pointers in Rust. While that is technically not true, for purposes of almost every Rust application you're going to write until you start working with unsafe Rust, that is true. The only way that we have to represent something that might be a null pointer, so to speak, is the option value. With Rust enumerations, some of the variants can accept parameters. In this case, we have 2 variants, one of them being none to represent that there is no data present, and the other one being some to represent that there is data present. Some requires that you store the data within the variant. And additionally, the option is parameterized over the data type. In the case of option, it can be almost any data type. The only requirement is that when you declare that you want to use an option, you specify the data type that you want to be storing in there. Building up one further, the result data type is our foundation for Rust error handling. Any function that can fail is going to return a result. In this case, we have 2 parameters, or 2 type parameters, one of them to represent an OK result and the other to represent an error result. And then we have corresponding constructors, one being OK and the other being error. Now, a few minutes ago, I said that if you wanted to construct a value or an enumeration value, you had to namespace it. However, there is an exception made for option and for result, in which all of the variants have already been pulled into the global namespace, and so you can access just the variant name without needing to specify that it is a variant on the result data type. This isn't really done by anything particularly magical in the compiler. It's simply some extra directives or some extra compiler directives that were given in the standard library. With this, We're going to want 3 separate fallible constructors. Each one of them results either a temperature, or results with either a temperature or an error. So jumping back into the code, let's implement these. First of all, let's create our enumeration. This one has three separate variants. We're going to add a couple of derivations for this one as well to make it easier to work with. First of all, we make it clonable. We have to, the automated test code forces us to have a debug representation and a partial EQ representation. Having done all of this, we jump down. We'll start with from k. We'll say result, temperature, comma, error. And then here, if k is less than 0, we return. We're going to do an early return in this case. Error, ERR is the name of the variant. And then here, because we're using the return keyword, we do need to include the semicolon, because return itself doesn't return, so to speak, anything. It just jumps you out of the function. Finally, we have changed the data type here. Temperature is not a type of result temperature, so we need to wrap it in an OK value. We save this, and things are failing. What is failing is on line 70, the test no longer works because from k is now returning a result, but we're still comparing against just a bare value. This is a case where also the compiler is able to notice a very common error pattern and make a good suggestion. So we'll jump down to line 70, and we will fix this with OK. And this one, line 71, we will fix by saying error. So we are asserting that the result of temperature from k minus 5 is going to be below absolute 0. Save that, and our test is back to passing. So with that done, I'm going to go ahead and uncomment these tests and then implement from C and from F. Now, with that done, our tests are passing. Now, there is one thing that is annoying me, and that is this right here. The math errors that get involved with doing division are giving us a negative Kelvin value, and that's been annoying me for a while. So instead, I'm going to fix it. And in order to fix it, I'm just going to start out by asserting that the value is 0. And one of the solutions could be that instead of doing a direct comparison, I could do a comparison with possible error. But in fact, what I'm going to do instead is simply grab this formula, assign it to a name k, and then if k is less than 0, we're going to return, or we're going to say, let's see here. I'll say this: if k is, or if Kelvin is less than 0, then we're going to return 0. Otherwise, we're going to return Kelvin. Now, you'll note that I've got an if statement, which is returning a value in each of its branches. I can assign the result of this to a new variable, k. Whenever you're working with an if statement, or later on, as we'll see, a match statement, every single branch has to return exactly the same data type. Obviously, that also means it doesn't have to return a data type at all, but then at that point, every branch has to return nothing. Anything that returns a value can then be assigned. This is also why Rust doesn't have a ternary operator, because in fact, this entire line, this can actually be made into a one-liner, although I suspect when I save the file that the auto formatter is going to break it into multiple lines. We'll find out in a second here. It did not. And in fact, if I wanted to, I could do this, which I do kind of like. So we'll save that, and we are back to where we were. As for what to do once you get one of these errors, we'll talk about that later when we're working with the higher level application. The last thing that we need to do before we can say that our temperature data structure is really usable is we need to provide some instance methods. And here the syntax is a little bit different. These methods can only be called on a full instance of a temperature. So they're not just namespaced functions the way from K, from C, and from F are. For the most part, you're going to name the function in exactly the same way as you did before. Your first parameter is going to be the special ampersand self, and then we have the normal syntax for returning a value. This is pretty easy to, in this case, this is pretty easy to implement, but again, this is one of those places where I do make mistakes. So bear with me as I potentially make those mistakes. Coming into here, pub fn as f self. These functions can't fail. We already have a valid temperature. Every valid temperature can be turned back into a bare F32. Now, if I were to save right now, of course, everything is going to fail because all of these functions are supposed to return F32s and I'm not returning anything. But I'm going to leave it like that for a moment so that I can go and activate the auto test that verifies that I don't make a mistake. I'm also going to go ahead and activate this auto test, which checks for absolute zero. The Kelvin one, truly trivial to implement. We just say self.Kelvin. That's it. It's done. In this case, we need to do some math. Self.Kelvin minus 273.15. And in this case, we do even more math. Self.Kelvin minus 273.15 times 9 divided by 5 plus 32. And I got it all right the first time. That's kind of miraculous. We have one last thing that we need to do before we leave this file. While the temperature data structure by itself is perfectly functional, we're going to be taking data from the command line, which means we need to do some string parsing. For doing that, I'm going to introduce traits, otherwise known as interfaces, if you are in a language which supports interfaces. If you could say that Rust has inheritance of any kind, this is the only way in which Rust has inheritance. It's only through trait implementations, and in some cases, traits have default implementations for their various functions. A truly trivial trait is the default trait. This is one that you can implement if there is a reasonable default value for your data structure. In fact, this one is so trivial that this is another one of those that you can auto-derive in many cases. If I were to implement the default trait for temperature, I would just default to either absolute zero or whatever the value for standard temperature and pressure are. There isn't really anything reasonable here, and we're not going to implement the default trait for temperature because we have another one that we will implement instead. The syntax for declaring a trait. First of all, you will usually want to declare the trait public. Once you declare a trait public, every single method which is declared on the trait is also declared as public. You use the keyword trait, you give it a name, you then give it the signature for every function that needs to be implemented. In this particular case, fn default doesn't take any parameters, and we are returning this capitalized self. Now this refers to, we're going to be returning self the data structure which we have defined the trait on. This will become a lot more clear in just a moment as we look at effectively trivial string parsing. The simplest string parsing that we have in Rust is based on this one trait from stir. Now this one also is a little bit more complicated because parsing can fail. There needs to be an error, and from stir introduces this idea of an associated type. So we are going to implement from stir on one type, in this case temperature, and we have to associate with the entire operation the error type. I can't really give you good rules for when you need to declare an associated type and when you don't. If you're defining a trait, unfortunately, that's something that I have a bit of an intuitive understanding of, but not sufficient to explain it. For our purposes, though, we don't need to get into the details. The only thing we do need to get into is that we're going to need to implement this function from stir. We're going to give it a string, or more to the point, any data type which implements the str interface. Most of the time that is going to be a string, but there are other types that could end up in here. And then finally we're going to return a result, which is either going to be a temperature or it's going to be a temperature error. Jumping into it, the way we start the implementation is we use the impl from stir for temperature declaration. So where this right here is saying that we want to implement temperature. In this case, we're saying that we want to implement from string or from stir for temperature. So we'll restore this. Now you'll note I have left most of this code, or I pre-wrote most of this code because it's not really particularly interesting to explain after we've already done all of this. The possible error type that can be returned here is just error, which is the same error that's being returned from these three functions. And then here's the implementation for the from stir function. I'll quickly save it just to get an auto format. There we go. Not ideal, but that's fine. And as always, got the wrong error type. Now, for the moment, I'm going to just to do this. And let's jump down and take a closer look at the test code that's involved here. Restoring this test, we can see that there are two different ways in which we're going to, string parsing most commonly happens. The first one, the more pedantic of the two, or the more explicit, you might say, is to use the from stir trait, the from stir function on the trait, and to pass it a string with 32f. In fact, you can also declare it like this, because from stir is now a function which exists on the temperature data structure. More commonly, you're going to see a string with the .parse call. .parse is a method directly on string. It just requires that whatever you are parsing to, this result type, implements from string. So long as it can figure out what you're trying to parse it into, it will type check. That's the type inference engine getting involved. If it can't figure it out, then you're forced to do this using this special syntax that we call the turbofish syntax, which is how we are, as the caller, explicitly telling parse what data type to return. If instead, though, what we were to say is like let a, which is a result temperature error equals 32f.parse. In this case, we'll be able to skip the turbofish syntax because over on this side, we're making it really clear exactly what we're wanting to parse. More often, though, for inline operations, we're just going to do this. So I save this. Obviously, we're getting not yet implemented because I left to do behind. Let's quickly add all of this code. And this is where we start adding quite a bit more. Now, the very first thing I want to do is if the length of the string is less than 2, we're going to just return an invalid temperature string. I'm doing this because there needs to, at least with this parser, there needs to always be at minimum one number and then one letter to represent what units this number is in. So once we've determined that this is long enough to be a parsable string, then we're going to jump in. We're going to figure out what the digits are, which I've defined as simply everything up to, but not including, the very last character in the string. After that, I can parse it as an F32 using exactly the same syntax that I already showed you before. F32 from stir, temp digits, and here is where we're actually going to handle an error. From stir itself could return an F32, but it could also return a parse float error. The rest of this code doesn't really want to deal with a parse float error, so we're going to return early. And the way we do this is we say, okay, we've got this match statement. We're going to, if the value is okay, we're going to extract the stored value, and we're going to return that from the match statement. So now this match statement must always return an F32. In the case of an error, we don't really care what the error is, but we are going to do an early return from the function of an invalid temperature string error. If we were not doing an early return, both branches here would have to explicitly match, or would have to exactly match one another. They would both have to return an F32, or they could, in theory, return a new result value, at which point our type for temp result is result F32, comma error. This one doesn't really make any sense for this function. There's nothing else that we can do, so an early return makes the most sense. Match statements have to be exhaustive, and so that's why this match statement becomes interesting. In this case, the nth character might not exist. There might not be anything there. So if there's nothing there, if there's a none, we need to return error invalid units. Like, I couldn't get a final character, therefore there can't possibly be units. Now this is a case where, because of this code up here, I'm pretty sure that this line of code can never be hit. And so it would make sense, in some cases, to put the unreachable macro in here. Now I'm not going to do that because I'm not entirely confident in my analysis, although I imagine that anyone looking at this will, or anyone else looking at this would just be like, no, obviously, Savani, that this line of code can never be reached. You're always going to have a last character. For these three, we have some f, the not literal, but the character f, which means that we're going to hit this line of code if we get back a character and that character is an f. We do the same for c and for k, calling different functions in each case. And then we have a final catch-all in which, okay, it's some other letter, or perhaps it's still a number, and we're just going to return invalid units. So that's how we do error handling. If there's a way to recover, we could also do recovery right here. In this case, there's not. We just want to return an appropriate error and let the user do something. In fact, we're going to print the error to the command line. With that, we have reached the end of our implementation of the temperature data type. Now it's time to do the last step. This last step is to give us a command line application that we can build. The steps for it, first of all, we need to get the temperature parameter from the command line. We need to parse it into a temperature, or bail out early and give an error message if it can't be parsed. We need to get the target units from the command line, and then we want to convert the temperature according to the units. We've already built all of the parts that we need. Now we just put them together in the application. First of all, cargo watch -x quote run. By the way, this command right here is going to depend a little bit on your shell, or it's going to depend on your operating system. Like, it can be, this one can be a little bit challenging. If you can't get the cargo watch to run, you can instead just say cargo run --100cf. It does mean that you'll have to run the command repeatedly. Of course, what it's done here, I mean, first of all, it's given me a huge number of warnings, because there's so many things that as far as it's concerned, aren't being used. If this were a library, then none of these warnings would come up. But it's not a library, it's a program, and so it expects everything that I've declared to be used. That said, it's not going to stop me from compiling. It just clutters up the output. And by the time we're done, all of these warnings should be gone. Cargo watch -x run 100cf. There we go. Cool. So right now the only thing it's doing is it is printing out the help, which is right here. It's just hard-coded in. Let's start out by getting the arguments. Now, this is not actually a list. This is an iterator. Every time we call the next function on args here, we're going to get another value until there are no values left to be gotten, at which point we start getting none. We could, if we wanted to, collect it all into a vector, but it is actually convenient in this case to get the values one at a time. So starting out, let's say match args.next, and because next returns an optional value, I'll have my editor go ahead and fill out the match arms. It can be either some or none. Well, if it's none, then we know that there's no parameter, therefore we know that we can't do anything. Let's just print help. And return early. Save that. Args has to be mutable. Any labels that you bind in Rust are immutable by default. Go ahead and make them mutable in the case where they have to do internal mutation, or you want to make changes. The next operation is going to change the args iterator because it has to change where internally it's pointing. Now, in the case of sum, we know that we've got a value here, so we'll say, we'll just call it input, and then we'll say input parse, that's not right, input dot parse, a temperature, we'll assign that to maybe temp, because the parse could fail, and the type checker is figuring out what it is, so it's a result temperature error. So let's say match maybe, in fact, we'll say let temperature equals match maybe temp. Fill out the match arms again. If it's a T, or if it's okay, if it is a temperature, we're going to return T. If not, we're going to first print the error. I believe we can only use the debug syntax here. Then we're going to print help. Then we're going to return. Oh, invalid temperature string. That's unexpected. Converts 32. Why is... I'm going to go ahead and I'm going to print right here what maybe temp is. This is not going to help at all. Yeah, it just prints the error representation. I'll come up in here. And in this case, oh, that's the mistake that I've made. The very first parameter is the path to the executable that's being run. And although I am running the executable with a cargo watch whatever command, it knows that this on the file system is actually where the executable lives. So let's see here. We have a very easy function for doing this. Once we've constructed the arguments, we can skip the first one. Okay, now we can see that we're getting 100C. We're no longer getting an error. It's not doing anything because we're not doing a conversion. So I'm going to go ahead and remove the debug print that I put in there. Okay. So the last thing we need to do here is we need to figure out which units we're converting to and then call the relevant conversion functions. This one gets a little bit difficult because the syntax makes it a little bit challenging to get the units and massage the data types just right. So I'm going to do it in multiple steps. First, let units equals match args.next. We're going to fill out the match arms right quick. If we get a value, we're just going to return this. And of course, if we don't, we will say eprint ln. In this case, we get to write our own error message. So no units specified. And I mistyped eprint ln, help, and return. Let's quickly prove that works. So I've dropped the final destination units, and we've hit this line, no units specified. Units here is still a string, so we need to do one final step here. For reasons which would get very complicated and confusing to explain, we need to call this asRef function to convert from a string to a reference to an object that implements the stir interface, because that's what we have to do in order to match against string literals in a match statement. I'm going to go ahead and print ln. We're going to go ahead and print the result, starting with the first string. Oh, I didn't save the first string. I'm realizing here that in my original description and in the way that I want to print things, I still need a copy of the original string. And in fact, I didn't save that. So we're going to pause this for just a second. We're going to come back up here. And instead of parsing here, I'm going to do this, and then that's a bit better. So instead of doing the extract the argument and parse in a single line, doing it in two separate lines means that I can keep back the original string, and then I can just save the result of parsing the string. So coming back down to here, we'll uncomment this. We'll print temperature stir, which will be this first parameter, and then we will do temperature dot as f. Well, I am going to go ahead and, cannot do that. Need to do a comma. I'm going to go ahead and implement the other three. And then finally, the fallback, in case the destination temperature doesn't match any of the valid ones, invalid units specified. We will save, and now we can see that we are successfully converting from 100°C to 212 Fahrenheit. Similarly, cargo run, we'll say 100°C to K. which is 373.15 Kelvin. I don't happen to know, say, the freezing point of oxygen. I also know that command line parameters, it's very difficult to put minus signs into a command line parameter, so I can't actually write any negative values here. But we'll just say 50K, we want to convert it to C, and that's really cold, and I don't want to ever encounter that. Probably freeze solid in a couple of seconds. Now that is where I'm going to bring our talk to a close today. Some advice for going further. You can pick up the Rust book, which is available for free online, just a bunch of HTML pages. You can also pick up Advent of Code and attempt to solve the Advent of Code problems in Rust. That's actually how I learned Rust for the first time many years ago. If you want to contact me directly, there's a variety of different ways. I try to stream on Twitch once a week. I don't always succeed, but if I do succeed, I'll be streaming on Monday nights at 9 p.m. Eastern. I'm available for direct communication on Matrix, Discord, Mastodon, and you can even email me if you are still inclined to use email. I still use email quite a lot. In future talks, I'm going to go over the memory model. I will also go more in depth on any other topic which has become of interest to me. On my YouTube channel, you will be able to find a presentation that I did a couple of months ago in which I implement drag and drop interfaces using a React-like web framework written entirely for Rust. This has been a very long presentation. Again, it's just an overview. I don't actually get to the memory model in this, even though the memory model is probably the hardest part. I'll cover that in a future talk, like I just said. If you've gotten this far, thank you for watching. If you have additional things that you would like to see me talk about, leave them in the comments, send me an email. Thanks for watching. Have a good day.